All right. Okie doke. So where we left off last was taking a look at this formula CH3OH and seeing if we could come up with a Lewis structure for that. And just before we stopped recording, I said, well, the reason why they have it listed like this is because, go back, find where I was. Sorry about that. My hand touched a part of the screen here. Come on. Yeah, is because we know that the CH3 is connected, right, to the OH like this. Okay, well, if we have that in mind, then it shouldn't be that much of a stretch to say, well, we know that carbon has 4 bonds. 1, 2, 3, 4. We know it's connected to the oxygen. Oxygen always has 2 bonds and 2 lone pairs, so we have 1 bond. And hydrogen always has 1 bond like this. So now you can see that we've used up 1 carbon, the only carbon, 1 oxygen, the only oxygen, and 1 of the hydrogens. We have 3 left. Where are they going to go? Here, here, and here. Now, based off of this drawing, if I tally up the total number of valence electrons I've used up, I'm supposed to have a total of 14, but I've used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 4 electrons missing from my structure. Could anybody tell me where they go? Where did the last 2 electrons go? That's right, they go in the oxygen, because we know that oxygen always has 2 bonds and 2 lone pairs, right? Just think of water. The oxygen has 2 bonds and 2 lone pairs. So there you go. That's our answer. And this compound, this is methanol. Methanol or methyl alcohol. Anyhow, the name's not important, but I like to share names with my students along the way, just so that when we get to nomenclature, it's not a big mystery to them. They've seen a few names along the way. So if we look at those 2 structures, there's no charge on any of the atoms in there. But if you think back to your general chemistry days, right, you talked about things like a chloride ion, right, that has a negative charge, or a sodium ion that has a positive charge. Well, how do we look at a Lewis structure and assess what the formal charges are on atoms in there? Well, before we do that, we have to define what an anion and a cation is, and I'm pretty sure you all remember this very, very well, that a cation has a positive charge. It's an atom with a positive charge. And an anion is an atom with a negative charge. One of the mnemonics that my students gave me years ago is an anion. They kind of make an anarchy symbol, you know, for the negative charge, and then a cation. Well, if you think about cation, if you just draw a circle here, kind of looks like a positive charge around the letter T like that. If that helps you, great. If not, I don't know what to tell you, I guess. But anyhow, the way that we calculate formal charge, according to our textbook, this is the formula that he uses. He says formal charge, we take the total number of valence electrons, we subtract the total of the non-bonded electrons plus the number of bonds. But I have an easier way of doing it. And my way is this. I say formal charge, Fc, is equal to the number of valence electrons. So we take the total number of valence electrons, we subtract the number of sticks, and we subtract the number of dots. So dots are dots are unpaired electrons, or lone pairs, and sticks are just bonds. So let me show you, okay? If I look at the aluminum in AlH4, how many valence electrons, let's try this again. How many valence electrons does aluminum have? Anybody? How many valence electrons does aluminum have? It's in group 3A, right? So it has 3 valence electrons. So we take 3 valence electrons minus 4 sticks. 1, 2, 3, 4 sticks. Minus, there are no dots on the aluminum. So 3 minus 4 minus 0 gives you -1. So that tells you the aluminum has a -1 charge. Is there any charge on any of the hydrogens? Anybody? Do the hydrogens have charges in here? In AlH4? No, right? Because they all have 1 bond, right? We could test it. Could test our hypothesis. So we could say hydrogen has 1 valence electron minus 1 stick minus 0 dots, which gives us 0. So the hydrogens have no charge, right? Hydrogen only has one bond. Now, let's try it one more time here. If we look at this oxygen, oxygen has 6 valence electrons, minus 3 sticks, minus 2 dots, which gives us positive 1. So that tells us that the oxygen here has a plus 1 charge. Now, what I would like to do is give you guys a second. I'll give you 1 minute to see if you can find the formal charges in C and D. Okay, it's very difficult for me to not talk. But anyhow, I'll give you 1 minute to see if you can find the formal charges in here. Remember, give it the old college try. You're going to need a periodic table. So if you don't have one, chemistry class, print one out or use one on the internet or something. All right. Let's see, did the alarm go off? There we go. All right. Did anybody find a formal charge in C? And could you tell me where it is if you found one? Jennifer, I see you put a -1. Which atom did you say? Yeah, exactly. There's a -1 charge on the nitrogen, isn't there? So let's take a looky here. So I'll go back to my blue pen here. So nitrogen has 5 valence electrons, minus 2 sticks, minus 4 dots. That gives you -1. So yes, the nitrogen has a -1 charge on it. Absolutely. What about in D? Did anybody find any formal charges in D? Anybody find a formal charge in D? Yeah, on the oxygen. Yes, there's a formal charge there, isn't there? Okay. Oxygen, right? Think about it. Oxygen in water has 2 bonds and 2 lone pairs. This oxygen has 3 bonds and 1 lone pair. So that's not normal. And so we have 6 valence electrons for oxygen, minus 3 sticks, minus 2 dots, right? 1, 2, 3 sticks, right? Each line counts as 1. And so that gives us +1. So the oxygen has a +1 charge on it. All right, the carbon is fine, right? Carbon has 4 valence electrons, 4 minus 4 sticks and 0 dots gives you 0. So everything else is uncharged. So there we go. We have a formal charge of +1 on the oxygen in D and a formal charge of -1 on the nitrogen in C. All right, so that's how you calculate formal charge. I'll just tell you that by the time you've done all the practice problems and you've worked through this and that, students are usually very good at identifying formal charges and they don't need much coaching on that. So let's talk about polar bonds for a second and non-polar bonds and ionic bonds and what all those things mean and why it's pertinent to us as organic chemists. So first of all, electronegativity. What is the definition of electronegativity? Well, it's how strongly an atom attracts shared electrons. And so if they're shared electrons, it's implied that they're involved in a bond, right? They must be bonding electrons. Now, the reason that is relevant is sometimes students will ask, what's the difference between electron affinity and electronegativity? Because they're both how strongly an atom attracts electrons. Well, electron affinity is how strongly an atom attracts electrons when it's by itself, whereas electronegativity is when we have shared electrons, and it's a measure of how strongly an atom attracts those shared electrons, right? So Some electronegativity values that you should know, that you should have memorized, okay? The first one is hydrogen. You should memorize is 2.1. Then fluorine is 4.0, and then you should memorize the rest of the second period. And it's not that difficult to memorize it because as you go back from fluorine, which is the most electronegative element in the entire periodic table, which is 4.0, as you go from right to left, they decrease by 0.5. So oxygen is 3.5, nitrogen is 3, carbon is 2.5, boron is 2, beryllium is 1.5, and lithium is 1. Now for the second period, you could start with the sodium, which is 0.9, and then you see that they go up by 0.3. So you see it goes up by 0.3 to magnesium, 0.3 to aluminum, so we have 0.3, 0.3, 0.3 to silicon, 0.3 to phosphorus, and then it changes once you get to sulfur and chlorine, but there's another rule you can use for sulfur and chlorine, which is the over 2 and down 1 rule. So for carbon, which you already knew was 2.5, if you go over 2 and down 1, it's the same as sulfur. And for nitrogen, which is 3.0, if you go over 2 and down 1, it's the same as chlorine. That over 2 and down 1 rule only works for carbon and nitrogen and sulfur and chlorine respectively. But anyhow, it's pretty handy. So those are the values that I recommend memorizing, especially the second period and hydrogen. Now, another thing that's going to come up quite a bit is what is the most electronegative element? Well, you can see it says right here in my notes that fluorine is the most electronegative element in the entire periodic table. However, so we can even write down here, we'll write gold medal over, we will write first place. Okay, first place is a big deal, you know, being first place. But what is the second most electronegative element on the periodic table? Does anybody see it? It's not a trick question. It's on the screen. What's the second most electronegative element on here? It's an element that comes up a lot more than fluorine. Exactly. It's oxygen. Okay, so oxygen is second place. Okay, now you can't beat first place. Okay, first place is the winner. However, oxygen comes up constantly in organic chemistry, right? It's found in all kinds of biomolecules, sugars, RNA, DNA, proteins, peptides, amino acids, et cetera, et cetera. So oxygen is going to be very, very important. So remember that. Students usually remember from General Chemistry 1 that fluorine is the most electronegative element, but don't forget that oxygen is the runner-up. It is also very electronegative. Now, moving forward, how do you discern whether you've got a polar covalent bond or not? Well, you've got to memorize the difference between these three, okay? So you want to memorize this, that if you calculate the difference in electronegativity between two elements and it's less than 0.5, we consider that to be a non-polar covalent bond, okay? We just call it a plain old covalent bond. Now, the way that we measure difference in electronegativity is we use delta for difference and En for electronegativity. So that just means difference, delta, En, electronegativity. So if I was to do the carbon-carbon bond, I'd say delta En is equal to, well, each carbon is 2.5, so 2.5 minus 2.5 gives me 0. So there's no difference in electronegativity between these two. Now, what about the carbon and hydrogen? Could anybody do the math and tell me what the difference in electronegativity between these two is? And remember, we take the absolute value. So you can put the bigger number first. Could anybody tell me the difference in electronegativity between these two elements, carbon and hydrogen? It's not a trick question. Carbon is 2.5, hydrogen is 2.1. Exactly. So 2.5 minus 2.1, and we get 0.4, like that. So those are both less than 0.5, so those are considered to be covalent bonds, or you can also call them non-polar covalent bonds. Now, if you look at the difference between carbon and oxygen, in this case, the delta En, we know that oxygen is 3.5 and carbon is 2.5, so the difference is 1.0. Now, what's the definition of a polar covalent bond? When it falls in the range of 0.5 to 1.7 for the difference in electronegativity, when delta En is between 0.5 and 1.7, we say that is a polar covalent bond. So 1 falls in that range, and therefore this is a polar covalent bond. Besides knowing that this is a polar covalent bond, sometimes we as organic chemists put little delta symbols on top of the elements and then put positive or negative, meaning that which one is partially positive and which one is partially negative. So the delta in organic chemistry stands for partially. Okay, this is not a cation, this is not an anion, but the carbon is partially positive and the oxygen is partially negative. Now, sometimes students will say, hey, Mr. Dion, I remember in my general chemistry class, sometimes we would do this. We would say carbon and oxygen, and then we would draw a dipole going towards the more electronegative element. There's nothing wrong with that. That's perfectly fine. It's just another way of representing the exact same thing. Now, what if the difference in electronegativity between your two atoms is greater than 1.7? Well, then it falls outside of a polar covalent bond. Now what you've got is an ionic bond. Now, if you think about sodium hydroxide, sodium has an electronegativity. I'll scribble it down here. Sodium is 0.9, and oxygen, you remember, is 3.5. So our delta En is going to be 3.5 minus 0.9. That gives us 2.6. Wow, that's huge. That's way bigger than 1.7. And so the difference is so large, we say this is an ionic bond. So we have a full-on cation and a full-on anion. All right, give me a thumbs up if you're with me on polar covalent, non-polar covalent, and ionic. Everybody with me on that? All right, cool. And when I say that, it doesn't mean placate me. If you have a question, don't hesitate to interrupt me. But there you go. So those are the three types you need to know. The ones that we're going to focus on, let's face it, in organic chemistry are going to be non-polar covalent bonds and polar covalent. Is ionic still a thing in organic chemistry? Absolutely. We're just not going to cover it nearly as much. Okay, it's not going to come up quite as much. So going back to this whole idea of polar covalent bonds, we're going to use polar bonds to predict reactivity in organic chemistry. And so we want to take an even harder look at polar covalent bonds. So it says here that electrons tend to shift away from the lower electronegativity atoms to the higher ones. Now, again, here we said the delta En was nothing, so there's no difference in electronegativity. So they both have an equal ability to pull electrons towards themselves. Here we said the delta En was what, 1.0? Okay, we did that on the previous slide. Now, if we look at carbon and lithium, let's just write it in black here. It turns out that lithium has an electronegativity of 1.0. So we'll put here 1.0. I think I'm right. I just want to make sure. Yeah, it's 1.0. So our delta En here is going to be, 2.5 minus 1, which gives us 1.5. So it's a polar covalent bond. So that means that the carbon-oxygen bond is polar covalent and the carbon-lithium bond is polar covalent, but there's a big difference between the two, isn't there? Huge difference. You notice that in the carbon-oxygen bond, that the carbon is the more positive element, whereas in the carbon-lithium bond, the lithium is more positive. Well, why is that? It's because if you compare carbon and oxygen, the oxygen is more electronegative. And if you compare carbon and lithium, the carbon is more electronegative. Now, you might be staring at this right here and getting a little angry and saying, now, why did you draw that as a cation and an anion? You just told me on the previous slide that it has to be greater than 1.7 to be considered a cation and an anion. And the answer is, well, when it comes to electronegativity and determining whether something is polar, covalent, and ionic, you actually have to take the results of the calculation with a grain of salt, okay? So what happens is you actually get a transition going from covalent compounds, or covalent bonds, I should say. Where's my highlighter? From covalent bonds to polar covalent, all the way up to ionic, okay? There's no hard and fast line where it cuts off being polar covalent and becomes ionic. Okay, there's just, we see that something becomes more ionic as it has an increasing difference in electronegativity between the two atoms. So what that means is that sometimes you can write something as being covalent. So you can actually draw the bond between carbon and lithium as covalent. And then sometimes we're going to think about it as ionic, like this. Now, I was a student for a long time. I've taught thousands of students, so I can tell, or I can guess that there's probably somebody listening to me right now going, uh-oh, the whole quiz is going to be about me being able to figure out whether it's covalent or ionic. I don't know which one it is. No, 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 no. Okay. I would never try to fool you or trick you or anything like that. Don't worry about it. Okay. For the first quiz, we're going to take the values hard and fast. So what that would mean is that for carbon and lithium, the difference is only 1.5. So you would draw it like that as a covalent bond. Okay. The idea is this, okay? The reason it's in the textbook here is that because sometimes we do take these values with a grain of salt and we say, hey, we're actually not going to draw this like a covalent bond. We're actually going to draw it like a cation and an anion. But trust me, Mr. Dion will tell you when we're going to treat something as covalent and when we're going to treat something as ionic, okay? So again, in this class, our cutoff is going to be 1.7. We're going to treat something as ionic. Really, the only time that you have to worry about the exception of this is going to be in organic chemistry 2. Organic 2. And this is the first day of organic 1, so don't stress about it, okay? Don't worry about it. So again, you've got it on recording, okay? It's on the internet. So where was it? Can't even find. Here we go. These are the values that we're going to use. Less than 0.5, it's non-polar covalent. Between 0.5 and 0.7, it's polar covalent. And if it's greater than 1.7, we're going to say that it's ionic. Okay. But all this slide is telling you is that sometimes later on, when we get heavy into reactions, we start looking at different ways that compounds can react. We'll look at a covalent bond and say, well, imagine if it was ionic, how would it react in that case? Okay. All right. So now that we've got some idea as far as differences in electronegativities go, and we're aware of what a delta positive and delta negative symbol. Remember, the delta just means partially. Okay, we're going to see if we can scribble in some delta negatives and delta positives on this on these two compounds. So let's start with this one here, B. Let's see here. We've got fluorine, chlorine, and carbon and hydrogen. What I'm going to do is I'm going to write down the electronegativities of all of them because I don't figure that you've got them all memorized right away. So fluorine is 4.0, chlorine is 3.0, carbon is 2.5, and I know you have hydrogen memorized as 2.1. So based off of this, and again, we're just starting the subject. There's no trick questions. Could anybody tell me on this guy? Give me an idea where I might put a delta negative. Which atom do you think would have? Yeah, absolutely. Thanks, Jennifer. Absolutely right. Jennifer's saying, well, I know that fluorine is the most electronegative element in the whole periodic table. So she's saying, if I think about this bond between the carbon and the fluorine, the delta En is going to be 4.0 minus 2.5, which is 1.5. So she knows that that's a polar bond. And that's why Jennifer would say, well, I'm going to put a delta negative here and a delta positive on my carbon like that. Is there any other place that you might put a delta negative? I'll give you a clue. There's one more place that I would put a delta negative. Which atom would it be on? Would it be on the chlorine or the hydrogen? And it's not a trick. Which one do you think would take the other delta negative? Yeah, absolutely. It's going to be the chlorine, isn't it? Right? Delta negative for this guy too, right? The difference in electronegativity between chlorine and carbon is 0.5. So we said less than 0.5 was non-polar covalent. We said between 0.5 and 1.7 was polar covalent. So there you go. Nothing wrong with that. Now, you could draw the molecule that way and put delta negatives and delta positives. But if you guys will just allow me a second here, you could also do something that looks like this, where you could draw dipoles. You could say I've got a dipole going this way. I've got a dipole going this way. Like that. That would work too. Either one is fine. All right. So let's try this one over here. This molecule I'm sure you've heard the name before. This is acetone. Acetone, which is nail polish remover. All right, so acetone. There aren't an abundance of polar bonds in here, but there's at least one. Could anybody tell me where you might put a delta negative in this compound, in acetone? Which atom could I put a delta negative on? Don't be shy. We're just learning the subject. If you get it wrong, it doesn't matter. We're just fleshing out the ideas. Thanks, Jenny. Absolutely. Yes. Put it right there in the oxygen, wouldn't I? Right? And then I'd put a delta plus on this carbon. Now, there are no other polar bonds in this entire molecule, right? This isn't a polar bond because the two carbons have the same electronegativity. We know a carbon-hydrogen bond isn't polar. Carbon is 2.5, hydrogen is 2.1. The difference is 0.4. That's less than 0.5. It's non-polar. So therefore, this is the only polar bond in the entire molecule. All right. I want to see if I can test your, I don't like that. I want to see if I can test your memory of General Chemistry 1. I'm just going to stick this up here like that. If I take a look at this compound, the first one, okay, could anybody tell me what the molecular geometry of this compound be when the carbon has 4 single bonds? Carbon has 4 single bonds. What is the molecular geometry? Yeah, absolutely. It's going to be tetrahedral, isn't it? Okay. So what that means is that you're going to have the fluorine maybe up here. You're going to have the chlorine over here, and then you're going to have one hydrogen in the back and the other one out front like this. Okay, so going back to the idea of polar bonds, you know you've got a dipole going this way, and you've got a dipole going this way. And so if you tally those two dipoles together, what you get is a net dipole going in this direction. And so is this molecule polar? Yes, absolutely. This would be a polar molecule. We'll get into this in more detail in just a second, but I did want to refresh your memory that you do have to know molecular geometries for this class. All right, the next couple of sections about atomic orbitals and valence bond theory and molecular orbitals. I'm going to go over this kind of quickly. I only have a couple of slides on each of these because we actually don't go into a ton of detail on this in Organic Chemistry 1. In fact, if I just blast ahead in my slides, you'll see that when I get into MO theory, it actually says in the slides, we're going to talk about this more in Organic Chemistry 2. But I do want to go over some of the concepts with you that you do need to know for this class, okay? So if you remember when you discussed the atom and you talked about the Bohr atom and then you talked about the Schrodinger equation and how he came up with the orbitals, right? So first you started it with the orbits, right? You had n is equal to 1, n is equal to 2, so on and so forth. And then you had the orbitals. So could you guys tell me what type of orbital this one is here? If I put an arrow to this one here, what type of orbital is represented by this shape that I have here? It's described by a letter of the alphabet. What type of orbital would this be? The one that I have the black arrow, exactly, that's an s orbital, right? It's an s orbital is a sphere, right? These three orbitals here, they all have kind of that dumbbell shape. Could anybody tell me what type of orbitals these are? These are p orbitals, absolutely, right? P orbitals, okay? Now, the d orbitals and the f orbitals, we're not really going to look at those a whole lot in this class, but you do need to know that an s orbital has a spherical shape and a p orbital has this kind of propeller or peanut shape, right? You have the py, this is the px, and then this is the pz here. So there's 3 types of p orbitals, but there's only 1 type of s orbitals. Now, where did these come from? It says here that quantum mechanics was used to uncover the atomic orbitals that we have shown here, the s orbitals, the p orbitals, and of course the d and the f orbitals as well. But these are the solution to something called the wave equation, which requires complex calculus to solve. And obviously you don't have to take calculus in order to take organic chemistry. And so we won't be looking at that, but you do need to know the shape of an S. So again, an S orbital is a sphere. Okay, and p orbitals have kind of this peanut or propeller shape or a dumbbell, whatever you want to call it. Then you need to know that what is an orbital? An orbital is a region where there's a 90% probability of finding an electron, okay? So remember, electrons can move very quickly, but if I was to try to animate it here, and I can't really do it, but if you were to say, okay, here's your electron, the electron is going to be somewhere inside this space, moving very quickly, but if you average it out, eventually you get this kind of shape, okay? So that's where the electron is 90% of the time. When we have orbitals that have the same energy, we say that they are degenerate. Doesn't mean they've committed a crime or anything. Again, same energy means degenerate, okay? Those two words are identical in chemistry. Same energy and degenerate, they mean the same thing. And then, of course, you have to know, you guys all passed General Chemistry 1 and General Chemistry 2. So, of course, you have to know electron configuration. You have to know the Aufbau principle, the building up principle. You start with 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, so on and so forth. You need to know the Pauli exclusion principle, which means if you have two electrons in the same orbital, right, that one is going to be spinning up and the other one's going to be spinning down. And then you also need to know Hund's rule. And Hund's rule is, let's say you have, three degenerate 2p orbitals. You have them all half filled, right? You put one electron in each orbital before you start doubling them up, right? Sometimes I call this the bus rule. I won't go into why today. But anyhow, you need to know those three rules that you would have learned in General Chemistry 1. Now, in terms of valence bond theory, how do atomic orbitals overlap? Well, there's two types of bonds that we're concerned with as chemists, okay? One is a sigma bond, so a sigma or a sigma bond, okay? A sigma bond is a single bond, okay? Does anybody know what the other type of bond is? You have to know sigma bonds and pi bonds. Exactly, you have to know pi or pi bonds, okay? Now, if you don't remember which is which, here's the answer. Let's say we look at that molecule, this molecule that we looked at earlier this morning. We made a Lewis structure for this compound. It had a double bond in it. Okay, so here's the answer. The first bond between any two atoms is a sigma bond. So this is sigma, 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 sigma. After the sigma bond, the second bond or third bond between two atoms is a pi bond. So that means this is a pi bond. There's always somebody who raises their hands and says, well, would it matter if I put the pi on the top and the sigma on the bottom? No, it doesn't matter. You could say this one's the pi, this one's the sigma, but repeat, the first bond between two atoms is a sigma bond. The second bond is a pi bond. Now, what we're going to focus on in this section here is going to be sigma bonds. So sigma bonds, okay, understand sigma bonds. Well, how do you get a sigma bond? There's three scenarios that we're interested in. One is when you have two s orbitals overlapping. So this is an s orbital, this is an s, right? S is a sphere. Well, if they overlap, okay, that makes a sigma bond. So this is a sigma bond. Now, if you were to take a cross section of this, okay, and then you were to look at it with your eyeball, okay, of that cross section, what you would actually see is you would see a circle, right? You'd see a blue circle is what you would see, as if you took a cross section of that. That means that you've got a sigma bond. So when you have two orbitals overlapping and you take a cross section and you get a circle, that is a sigma bond. And if you're asking, so here's the circular cross section, right? If you were to take a look at this part with your eyeball, okay, what would you see? You would see this blue circle shaded in. So we call that a sigma bond. Now, as far as what are the other ways that you can make sigma bonds, I don't have it in the slides here right now, but I'm going to tell them to you, okay? The other two ways you can make sigma bonds are to have an s overlapping with a p. So let's say we have an s orbital, which looks like this, and a p orbital that looks like this. If we have the head of a p orbital overlapping with an s orbital, so I'm going to do a little animation for you here. The one on the left is the s, the one with the little dashed line going around it, that's the p orbital. If they overlap like this, that is a sigma bond. Right? If you were to take a cross section of this, you would see a circle. So that's the second way. The last way that you need to know is if you have two p orbitals overlapping head to head. So there's a p orbital, there's the second p orbital. Okay, we took one of these p orbitals and we overlapped it with another. This would also be a sigma bond, right? Because you get, if you took a cross section here, you'd end up with a circle. Now, could anybody answer this for me? Where does a pi bond come from? How do you get a pi bond? We'll scribble it in over here. Where do pi bonds come from? They don't grow on trees. I'm being silly. Could anybody tell me, where do you get a pi bond from? A double bond, yeah, but what kind of orbitals overlap? Not two sigmas, it's two p orbitals. Exactly, exactly. So a pi bond comes from this. When you have one p orbital and another p orbital, okay, and when they overlap side to side, like this, look, when they overlap like this, that is a pi bond. That's where a pi bond comes from. Pi bond. It comes from the side-to-side overlap of two p orbitals. Okay? So now, and if you take a cross-section of that, so if we were to take a cross-section, you can see you do not get a circle. You'd actually get two circles. You'd have one up and one low like this, okay? So sigma bond, you get one circle. It comes from the head-to-head overlap of two s orbitals, an s and a p. So this is an s, this is a p. Two p's overlapping head-to-head. Or if they overlap side to side, then you get a pi bond. There you go. So now you know where all the bonds come from. Now, as far as MO theory goes, again, we're not going to look at this in a whole lot of detail in this class, but you would have covered it in General Chemistry 1. I know because I taught General Chemistry 1 this semester. And if you remember, there was a part in General Chemistry where you talked about all kinds of funny molecules like H2, He2, Li2, right? N2, O2. Who remembers talking about all those? And then you had sigma and sigma star and then pi star. Is anybody, give me a thumbs up if you remember that from general chemistry. Anybody? Okay. So you would have learned a little bit of molecular orbital theory in general chemistry. So if you remember the orbitals that didn't have a star by them, those are bonding orbitals. And the ones that had stars by them, those are called antibonding orbitals. Now, as far as molecular orbitals go, all they are is this, okay, is that sometimes we can use atomic orbital theory to explain reactivity, structure. However, sometimes it's inadequate. Okay, so when it's inadequate, then we have to use a different model. And sometimes that model will be molecular orbital theory. And what molecular orbitals are is this, is that atomic orbitals only reside on a specific atom, whereas molecular orbitals cover an entire molecule. So they're much more complex, okay? They can be very, very complex. But the idea is this, is that they're a more complete analysis of bonds because they include both constructive or bonding interference and destructive interference. And so, again, we're not going to use this a whole lot in organic chemistry 1. So I'm just going to move on into things that are going to be pertinent for us in this class. So I guess the main thing that you would need to know is that the number of the number of atomic orbitals is always equal to the number of molecular orbitals, and that when atomic orbitals overlap, so these are atomic orbitals here, s orbitals. Okay, when they form molecular orbitals, however many atomic orbitals you have, here we have a total of 2, it gives you the same number of molecular orbitals, 1, 2. So in this case, we get 1 bonding and 1 antibonding. The bonding molecular orbital is more stable and the antibonding orbital is less stable. That's pretty much all you need to know. All right, let's get into hybridization for a second here. What's going on?